Today I want to talk a little bit about membrane potential. One of the things that makes neurons unique compared to other cells is that they have a difference in electrical charge on the inside of the neuron compared to the outside fluid surrounding the cell. So here's our theoretical typical neuron, right? And we're just going to kind of zoom in on a chunk of the axon here. Okay? And we'll draw like a cross section of the axon. The inside of the neuron is more negative compared to the surrounding extracellular fluid. Okay? And Neuroscience Online says that the inside of the neuron is minus 60 millivolts. Carlson, I think, says the inside of the neuron is minus 70 millivolts. Regardless of which of these numbers you choose, what it means is that if you take an electrode and you record just outside the neuron and just inside the neuron, what you'll find is a difference of between 60 and 70 millivolts. And this is when the neuron is not receiving or sending information. So this is what we call the resting membrane potential. When we talk about membrane potential in general, we often refer to it as VM, the volts across the membrane. So then VM rest would be the resting membrane potential. In addition to having this difference in charge across the membrane, we also have a difference in concentration of some of our major player ions. The three major player ions are sodium, which is a monovalent cation, potassium, also a monovalent cation, and chloride, a monovalent anion. Cation meaning having a positive charge, anion meaning having a negative charge. And I will tell you a funny way of remembering it that my high school chemistry teacher told us, which is that a cation you can think of as a plussy cat. So there you have it, plussy cat, cation. All right, let's go back up here. Okay, so we have this difference in electrical charge on the inside from the outside of the cell, and we also have difference in concentration of these major player ions. Oops. So let's start with sodium. It turns out that we have a lot of sodium outside the cell and not a lot of sodium inside the cell. The opposite is true for potassium. We have a lot of potassium inside the cell and not a lot outside the cell. In chloride, we have a little bit more outside the cell than we have inside the cell. Now what this means, because we have this difference in electrical charge and this difference in concentration gradient, it means that we have a lot of potential energy stored up in our cell. There are forces that make the ions want to move in different directions based on their charge and their concentration. So let's talk about that next. Okay. The two driving forces are electrostatic pressure, which is movement based on charge, and diffusion, which is movement based on the concentration of the ion. So let's draw our neuron again. This is a cross section of an axon. And again, we're at minus 70 millivolts. And let's take our example of sodium. We have a lot more sodium outside the cell than inside the cell. And we have a negative charge on the inside of the cell relative to the outside of the cell. So movement based on charge means that this positive ion is attracted to the negative inside of the cell. So the driving force of electrostatic pressure wants to push sodium into the cell. Diffusion is movement based on concentration. Ions want to move down their concentration gradient from a high concentration to a low concentration. So for sodium, the force of diffusion wants to push sodium into the cell. Okay, now let's do the same thing for potassium. For potassium, we have this big concentration inside the cell and not much outside the cell. But let's look first at electrostatic pressure. Based on just electrostatic pressure, ignoring diffusion, this positive ion, just like sodium, is attracted to the negative inside of the cell. So if we ignore diffusion, electrostatic pressure wants potassium to go into the cell. However, we have a lot more potassium inside the cell than outside the cell. So diffusion would push potassium from a high concentration to a low concentration. Now let's look at chloride. For chloride, we have a higher concentration outside the cell than inside the cell. This is a negative ion. So if we look at just electrostatic pressure, the negative ion is repelled by the negative inside the cell. Electrostatic pressure would want to push chloride out of the cell. Diffusion, again, is movement from a high to low concentration. So if we just look at diffusion, that would push chloride into the cell. So we ultimately need to know what direction an ion would actually move if a neuron became permeable to it.